Thank you, the organizers, for having me. It's a great pleasure to be back in Bangalore. Today, I'm going to share with you some of our work on quantum simulation using noisy Clifford circuits. In the morning, we heard the talk from Austin, and sort of that set up the stage very nicely for the kind of stuff I'll be talking about. So quantum simulation, as many of us know, that goes back 40 years. The sort of conceptual idea was proposed maybe by Feynman. And the idea to study quantum physics on a computer was quite novel at that stage, because a lot of the things that we now know in quantum many-body physics, like interesting ground states and interesting dynamics, that kind of knowledge was not available to Feynman, and yet he could foresee that a machine, you need a different kind of machine to study quantum physics. So it was quite a novel idea, and that has been a big effort in large part of the research in quantum physics in the past several decades. So when we jump 20 years later, there was a great leap in our understanding of quantum many-body systems when we started to realize these interacting many-body systems in cold atom experiments, which are using optical lattices, and sort of first step towards analog quantum simulation, where we, even though we don't have complete control on the many-body states, it was an important proof of principle that some of these many-body states can be realized in a sort of engineered setting. But there were several limitations that these systems have. These are sort of non-universal systems in the sense that if you have to study bosons, you need a bosonic, you have to use bosonic atoms. If you need to use fermions, you have to have a fermionic atom. On a classical computer, we don't have such a distinction. We can sort of study all kinds of classical physical problems on a classical computer. But this kind of analog quantum simulation was not sort of amenable to that, to the universal study of quantum many-body systems. These were also non-equilibrium systems, so that threw up a different set of challenges. And one of the sort of main sort of stumbling blocks for us for realizing sort of more interesting states of matter was that they were short time, they were sort of not long-lived systems, so you can't study the sort of equilibrium state, and they were too hot. So there was a lot of entropy in these systems. So one of the advances in quantum simulation was to be able to cool these systems by analog means and go down to lower temperatures, in some sense removing entropies from the system. And there was a limitation, which is a physical limitation, maybe not a conceptual one, how much entropy you can remove from these many-body systems which are coupled to an environment. So then we jump forward another 20 years. So now we are sort of in a different era of quantum simulation where we have gate-based experiments, where experimental systems which can apply a certain class of universal gates, and you can simulate you can sort of simulate many kinds of quantum many-body dynamics using gates on qubits. Of course, this gives us certain level of universality, because now you can study spin-half systems. Qubits are typically spin-halves. In principle, though, could be sort of spin 3/2. You can hire spin objects. And also, one can probably study fermions and bosons on the same physical platform. So there is a certain degree of universality in these systems. But there's still the problem of entropy, which we are still sort of grappling with, even in these gate-based systems. So they are also suffer from this. I mean, as we have sort of come to realize, they are extremely noisy physical systems. So they generate a lot of entropy. So in order to create interesting quantum states that we can sort of prepare and analyze and tinker with, we are still faced with a similar challenge of removing entropy from these systems. And they are actually quite small. I mean, current size of these gate-based quantum simulators are tens or maybe hundreds of qubits, while the analog quantum simulation has 100,000 atoms. So when we reach at the level of 100,000 qubits, removing the entropy from these systems will again prove quite challenging. So the kind of questions like Sarang talked about and Rosario talked about yesterday about in the presence of dissipation, how to prepare quantum states are quite important. And that has been sort of the excitement in the last few years, how sort of dissipation affects the quantum dynamics in these systems. So this is the main sort of workhorse of my talk. I'll be studying circuits of a specific kind, which I'll define later. But the aim is that what are the class of physical phenomena that one can study in this circuit setting, where you have qubits, sort of 2-qubit or multi-qubit gates interspersed with measurements. And this can have various universal characteristics. And the aim is to sort of motivate, find useful anchor points which are easier to analyze theoretically for evaluating quantum many-body properties. So in the morning, Austin talked about dual unitary circuits, which are a class of unitary circuits which can be useful for analyzing certain kinds of quantum many-body phenomena. And I'll try to argue that Clifford circuits provide another sort of another limit of these quantum circuits, which are easy to analyze and are useful starting points to study quantum many-body dynamics. So let me define Clifford circuits. So it's a set of unitary operations, which again act on qubits, so that we have n qubits in the system. And it's a set of unitary operations which take Pauli's operators to Pauli operators. So you have an n, so you have a Pauli operator defined on n qubits. So it could be a string of Paulis, sigma x's, sigma z's, and sigma y's, and our identity. And the group involves unitary gates, which take you from one Pauli operator to another string of Pauli operators. And once we limit the set of gates that we are studying to this particular subgroup, the states have a very simple, easy to represent classical representation in terms of these stabilizers. So states, so we consider only subspace of states which are stabilized by a set of operators. For each state, n qubit state, there are n stabilizers, and the stabilizers are a string of Paulis. So to define a state, we just have to define these n operators, which are a string of Paulis given by product of, so these are, so OI is a particular sort of operator, stabilizer, which could be a sort of, you could have the X operator on site 1 or Z operator on site 1, and so on. There's a sequence of X's and Z's. And one can have, whether you have that operator present at that site is given by this index nu I and mu I. So these indices essentially become like your degrees of freedom. So they define a phase space in which the dynamics of the system is sort of defined. And that sort of simplifies the problem a great deal, because now you can represent a many body state over 2 to the power n dimensional Hilbert space in terms of just these n, these are either zeros or ones, so in terms of this sort of a binary vector. So you've taken the problem of a many body Hilbert space, which is 2 to the power n dimensional, and reduced it to just describing the evolution of these n indices. So that's in spirit very similar to integrable models, where we have, if you have the integrals of motion, the integrals, you just have to keep track of the integrals of motion, and that tells you about the dynamics essentially. But here these are not quite integrals of motion. They are evolving in time depending on the dynamics you impose on the system, but they are still at any instant of time. They are easy to represent classically. So yeah, so you can represent states as a function of time efficiently by going to this representation and restricting oneself to a class of unitary gates. And that obviously you don't get a free lunch in this business. So that reduces certain class of problems. So yesterday we heard from Wenwei that there are sort of deeper notions of thermalization, which require you to study these highly non-local properties of the dynamics. Those properties will not be representable in such a circuit because it's essentially simple to simulate classically. So this because you just have to keep track of L degrees of freedom. So it's sort of something you can the dynamics is sort of simulable polynomially with L. At the same time, these form these sort of unitary operators represented by the Clifford group form a tree design when it comes to qubits. So if it's a tree design, a lot of averages of physical observables are actually equal to the Haar random case. So if you take correlation functions and even out of time ordered correlation functions, 2-point correlation functions, their averages will be the same as the average in the Haar random unitaries. So it's sort of, you've restricted yourself from sort of not able to study these highly complex states, yet at the same time, a lot of the physical phenomena may still be representable in these, using these simplified representation. One instance being that if you are, one of the things that we like to study in sort of quantum many-body physics is entanglement, and we associate volume law entanglement in pure states with some kind of thermalization phenomena. So that's somewhat physically the most chaotic system that we encounter in nature in some ways. And those kinds of volume law entangled states can be produced under these dynamics. Of course, they are volume law, but they may not have all the right higher order correlations. But maybe if you're studying physical phenomena, those higher order correlations are not important and we can throw them away in some, and this is one way of sort of neglecting those higher order correlations. So yeah, so another property is that they don't have any operator space entanglement because these operators always remain as product operators. You don't get a superposition of Pauli strings, so you're never quite generating huge amounts of, there's no entanglement in operator space. So yeah, so this will be sort of the sort of mathematical setup of all the phenomena I'll talk about in terms of Clifford circuits. So yeah, so I'll sort of aim to sort of convince you that there are various classes of quantum phenomena which we can study, and this idea of studying them using Clifford circuits gives us a useful handle of these classes of phenomena. So one class of phenomena which we really enjoy studying is hydrodynamics. How does hydrodynamics emerge from interactions in a many-body system? And that is possible. So I'll try to show you how if you take long-range interactions, which is usually a very hard problem to study in quantum many-body physics. So you can study long-range interactions and study how hydrodynamics emerge from the long-range interactions in these Clifford circuits. So, and how the range of the interaction affects the hydrodynamic behavior. The second class of phenomena that we quite like studying in quantum coherent phenomena is sort of localization. So this is where I connect with the theme of the workshop. I'll study Floquet systems. Floquet systems and disordered Clifford circuits, and argue that there is a genuine kind of localization which has quite distinct properties from Anderson localization, but also distinct from many-body localization, which can be studied using random Clifford circuits. And the last part of the talk, if I have the time, will connect with sort of pursue the effort to build long-range entangled states, similar to what Sarang was talking about, but using also sort of measurements and symmetry, symmetry operations. So that's where I'll put in measurements along with the first two parts will be all about unitary dynamics with no measurements, while the last part will include measurements to produce long-range entangled states and study the complexity of the preparation protocols. Yeah, so let me begin. So yeah, so the model, the first sort of phenomena that we look at is sort of studying hydrodynamics of a U1 conserving unitary evolution with some total SZ conservation. So this is we chose gates randomly from the Clifford circuit, Clifford group, and there's no structure in space or time except that in space it's a long range. So we choose 2 qubit gates and entangle 2 qubit gates randomly where the range, so the 2 qubit gates could be acting on any 2 pair of qubits, but the probability that 2 qubits are entangled or acted on by the Clifford gates goes down like a power law. So it's sort of analogous to power law interacting Hamiltonians, so to say. If one is interested in the infinite temperature hydrodynamics, then the energy doesn't matter. And the claim is that the hydrodynamic properties of this random circuit will mimic the hydrodynamics of an infinite temperature long range system with the same conservation law within this framework. And our results, I'll try to convince you that the results point in that direction, that the hydrodynamics that we get are sort of as expected. So yeah, so what do we do to study the hydrodynamics? One can study operator spreading, which Austin introduced in his talk. So one can start with an initial sort of Z operator, which is localized in the middle of the system, and ask, as you evolve the system under this random unitary circuit, how does this operator behave as a function of time? So yeah, so when alpha, which is now alpha is equal to 5, so which is relatively short range couplings between the qubits, this operator sort of performs a random walk and sort of spreads, performs a random walk. It doesn't spread in this case because of the conservation law. So because of the total SZ conservation, this operator remains a single body operator, but it does exhibit diffusion. So if one were to sort of map the profiles of the spreading of this operator, so if one were to ask what happens as a function of distance and time, you can sort of collapse the entire sort of spreading of this or the sort of motion of this operator onto a Gaussian profile, showing that this sort of exhibits diffusion. So this operator, single body operator, acts like a single particle and sort of moves around under the action of the unitary, and it produces diffusive behavior when the range of the interaction is relatively short range. So random walk, large alpha means random walk, which gives rise to diffusion. Now, as you reduce alpha, this operator now sort of starts having excursions far away, and the profile, the spatial profile is quite broadened, and one can, which sort of is consistent with Levy flight. So essentially the operator which acts like a particle, the single site operator, it sort of jumps far away and performs a Levy flight. And that is consistent with the sort of profile that one expects from Levy-Phi, some kind of Lorentzian profile, where this Z, now we have to, so this is for Z, in this case, for alpha is equal to 2 is equal to 1. So this is Z is equal to 1. And part of the effort will be to connect the entanglement growth in this circuit to this dynamic exponent of transport in the system. So yeah, so another quantity that is quite important for studying the sort of quantum chaos is the growth of these operator sort of, which is not conserved in this case. So if we take the X operator now, the X operator, because it's not conserved, it spreads ballistically, and you get this light cone behavior when the system is unconstrained. So if the system is unconstrained, so this operator grows ballistically, and you get for large enough alpha. So if it's short range system, then you get the usual of the light cone in the system. But when you go to sort of more longer range system, this light cone develops these tails, because it's sort of no longer short range interaction. So light cones develops these power laws, and these power law broadening of the light cone is so we'll quantify that sort of in terms of what is the exponent, how does this light cone depend as a function of time, scaling with z. So that is something that we'll quantify later on. Yeah, it's a continuous. So there is a critical alpha. I'll show in the. So at the critical alpha, it sort of becomes starts becoming super diffusive, and then at small enough alpha, it sort of becomes completely non-local. So this was for the unconstrained case. For the U1 case, this. So this starts at alpha is equal to 3. So alpha is equal to 3. This starts deviating from the diffusive exponent.
But are those the same? Like the two separate issues? First, when there's the unconstrained, the second is when the.
Yeah. So the unconstrained. So this is. So sorry. Yeah. Thanks for pointing out. So the unconstrained. There's no there's no. So dynamic. I mean, there's only one. There's only entanglement growth. But it also, the unconstrained case also has the same it goes from the unconstrained. The unconstrained goes from so it has a linear light cone, and at z is equal to alpha is equal to 2, it crosses over to having a power law in the thanks for pointing. So in the diffusive case, it changes to the exponent changes at alpha is equal to 3, while the unconstrained, the exponent changes at alpha is equal to 2. And this is due to the conservation law. And that you can, yeah. So there's a there's a subtlety here, because Clifford circuits, the entanglement in Clifford circuits, if you take the non-Clifford problem, then the entanglement growth actually of the von Neumann exhibits a different scaling from sort of the higher Renyi entropies, while in the Clifford case, because the entanglement spectrum is flat, the entanglement, so this is analog of entanglement growth, the entanglement growth is the same for all Renyi entropies and the von Neumann entropies. So the exponent is the same in that case. So while in the purely chaotic system, the von Neumann entanglement entropy will cross over at a different, will show diffusive behavior, even though the higher Renyi entropies will show ballistic. Diffusive. Or did I say von Neumann is linear? Yeah, that's right. Yeah, because it's Clifford. That's the.
Yeah, but I guess it's a bit counterintuitive. But maybe, so is it true that if I took an operator in the U1 circuit that was transverse, like an exponent y operator, wouldn't that grow holistically?
No, it sort of generates. It generates. It's not showing on. Yeah, the other one, I guess. Yeah, so your point was.
So is it true that, normally I'd have thought something like this, the Z operator is special because they don't really do anything.
Yeah.
Because it's better. But then the X and Y operators in principle aren't like that. Those would be growing pretty complex.
So that's because of the Clifford. I mean, they're mostly, when you generate, you're mostly generated Z operators. So yeah, so the X, yeah, the density of X, that's what this is showing. The density of X actually keeps decaying as a fraction. And the density of Z is, as time goes on, it sort of becomes, so you're dominated by Z. So that's the difference from Haar random. Haar random, you're sort of generating everything. So so here it mostly becomes, so the proportion of Z in the poly string sort of becomes, it's sort of mostly Z.
And the Z's themselves don't do anything.
Because of the conservation. And this is, yeah, basically, that's good. So yeah, so. Yeah. So yeah, so for in this sort of U1 case, for Z greater than alpha, for alpha greater than 3, you get this dynamic critical, the dynamic exponent behaves diffusively. So which is related to the entanglement, how the entanglement entropy grows with time, while the diffusion of the conserved quantity decays like 1 over square root t, while as you go to alpha less than 3, sort of decays, the dynamic exponent satisfies this linear behavior, alpha minus 1, between alpha is equal to 1 and 3. And that's sort of the entanglement and the decay, diffusive decay, or the dynamical decay is sort of satisfy this relationship. And so they are sort of coupled to each other in this way, the entanglement growth and the hydrodynamic behavior. And as you go to alpha less than 1, then the system becomes completely non-local. It behaves like an infinite range system. So it's almost, the entanglement growth is almost instantaneous. So yeah, so these properties, so one could study them in Haar random circuits, and one can find similar behavior of, basically the same behavior of the dynamic critical exponent. But maybe if you study fluctuations in the Haar random case, those will be different in terms of if dynamics of the fluctuations could be different in the Haar random, but from the point of view of just local observables and how diffusion takes place in local observables, that those are captured just like the usual chaotic system in these Clifford. Any other questions? Okay, so let me sort of go on to the second part. So yeah. So in the second part, we'll look at the Clifford circuit, which is a 2-layer Clifford circuit, which is brick layer, where now we are choosing random unitaries, two-side entangling unitaries randomly from the 2-qubit Clifford group, and running it like a flow case circuit as a function of time. And so in 1D, So again, now there's no conservation law. It's now periodic in time, and there is no conservation law. One can ask about operator spreading as a function of time using this flow case circuit. And as you evolve it in time, this model, this flow K model, although it's able to show volume law entanglement, one can show that it's strictly localized within some finite volume. So it's an interacting system. It's able to thermalize if you have long range gates and if you're time dependent. But in a time periodic circuit, if you choose the gates randomly from the 2-qubit Clifford group, then you have strict localization within a finite volume. And that's true for, so there's no tuning parameter in this model. This is just, you're just uniform, choosing uniformly from the set of gates. And that gives you strict localization, which is quite non-intuitive, because in an interacting system in 1D, even if you are many body localized, you do not get strict localization within a finite volume in operator spreading. In this case, you get strict localization within some finite volume due to some interference effects, which I will talk about. Yeah.
Should I just think about it as you're sampling Clifford at random, and therefore with some probability you're going to cut the circuit out?
So this is not cutting the circuit. So this is, the localization is coming from destructive interference. So there's some fraction of if that was the case, there would be realizations of the circuit where it won't be localized. This is localized with probability 1 in the thermodynamic limit. Yeah, so I mean, we can discuss that. But these are not coming from trivial cutting of the circuit, basically. So it's the probability of the string of gates which leads to. So let me explain that, and that will set the explain what. So because these are symplectic matrices, you can study time evolution. It just acts as an action of on these indices U, which are these sort of phase degrees of freedom. So these are like single particle degrees of freedom, and one is asking about interference effects between. So you have some range of gates, so which is being repeated, and for it to be completely localized, if you have an operator on site 0, at site there should be no weight at site 2, site 3, or anything afterwards for any subsequent time step. So if you repeat your flow case circuit, there should be the weight of the operator on that site will go to 0. So one of the conditions that needs to satisfy, you have to satisfy these two conditions for this to be 0 at site 2, because that sort of tells you that there is destructive interference of these operators as you go later on in time. And this is satisfied. So once only for the qubit case that this is satisfied for all times. So if you satisfy these two conditions, you're satisfying it for all times. So there's some kind of, and there is a finite density of these sequence of gates, basically. So which is different from the sort of trivial cutting of the circuit. So yeah, but what one can show that in 2 dimensions, this is not true, because now you essentially, the intuition is that if you start with an operator at some site and you ask about the propagation, there is always a path which will take you to the edge of the light cone in the system, because so you can do a random walk. There will be a finite probability that the operator will reach, some weight of the operator will be on the light cone at all times, while that is not true for the one-dimensional case. So the 2D case is always thermalizes. So yeah, so we looked at spectral form factors, and that has interesting properties. Shortage of time, I'll sort of skip this and move on to the last part. where we try to prepare long-range entangled states. So there has been recent interest in producing long-range entangled states using measurements, combining with unitary gates. So here is an example where one can, in one dimension, prepare a cat state, using unitary evolution, where you implement these unitary gates, two-site unitary gates, and then perform a measurement on a subsystem, which in this case includes even sites. So you perform this measurement in the X spaces on the even sites, and that projects you, prepares this long-range entangled cat states. And these are, cat states are sort of eigenstates of these symmetry operators. So there are two kinds of symmetry operators which the cat states satisfy. One is a local symmetry on the even sublattice, which is two-site ZZ operation, and there's a global symmetry on the odd side, two-site in the odd sites, and there's a global symmetry with spin flip on the odd sites. So yeah, so you have to measure in half the system, and these are all and evolve using this Clifford gate. This is a Clifford gate. So these are all Clifford manipulations, and the system is in this eigenstate of the cluster operator. So these are ZXZ operators. These are again Clifford gates. These are the stabilizer states for the entire evolution with this. So this is a two-step process. You can prepare a cat state in two steps, which is hard to prepare just by a unitary measurement. So this is sort of forms the basis for measurement-based quantum computation, where you can use measurements to prepare these entangled states. So what we looked at is now asking the question, what is the robustness of this protocol if you introduce errors? And what is the circuit complexity if you introduce errors in this protocol? So we took two kinds of errors. So to begin with, because we always wanted to prefer this sort of Clifford gates, so one can choose stochastic Clifford gates and measurements, and when you make the circuit stochastic, then this local symmetry operator, in the case where you have probability 1, obviously you just prepare the cat state in 2 steps or 1 step, but if you introduce some stochasticity in these gates, the time scale there's a sort of a long time scale which emerges. It's only at some late time that you get the cat state emerging from the evolution if you are evolving it stochastically. So this is, okay, you can't drive a measurement-induced transition. You can also drive a measurement-induced transition for a different set of gates. But in this case, the time scale, you get a long time scale for the emergence of the symmetry. So this is what we understood. So what is this time scale? Because that time scale sets how deep a circuit do you really need to prepare this cat state when you have errors in your preparation protocol. So now one can introduce errors in sort of the unitary part of the evolution or the measurement part of the evolution. So if you introduce errors in the unitary part of the evolution, one gets a time scale which scales logarithmically with system size. So you get, so there's some time it takes for these symmetries, which were initially not there after step 1 process, for these symmetries to emerge, you need some logarithmic in system size. While if you have errors in both of them, then you get a time scale which scales exponentially in the system size. So so the naive implementation of the protocol without any error mitigation will give you an exponential blow up of the circuit. So you need to do something clever to actually prepare these states in the presence of errors. So this is a picture. So there's a logarithmic time scale emerges because of these local symmetries take a logarithmic long time to emerge, while the global symmetry that I talked about takes an exponentially long time to emerge in the presence of errors. And we tried some sort of error mitigation protocols, but I'll leave that for a later discussion. Thank you.
All right, we had some questions, but probably time for a couple more. Yeah.
Sorry, I did not understand in the last part. You want to get the cut state with fidelity 1?
Fidelity 1.
So if you would allow just not 1, what 1 minus something?
So that time also
still-
scales with log. I mean, at least in one of the cases, scales logarithmically with L. Yeah. So, but in the so we would want with fidelity 1, fidelity. But even if you want 99%, it's depends logarithmically with system size.
I was going to ask something, but it may not be a short answer. Is there just a classical description of what's going on?
Yeah. So it's in this case, because of the Clifford nature, you can basically, you can see, I can explain to you.
Okay.
It's to do with the stabilizers.
Yes,
I mean, if you skip, it has the stabilizers and the measurements have to be occur sort of next to each other for these local symmetries to emerge. So that can explain the logarithmic, and the exponential is basically you randomly skip it, applying these two operations and
Percolation in one dimension.
percolation. Is it percolation?
Okay.
1D percolation.
Okay, you can explain it. Okay, good. Let us close this session, and I think it's back.